Hi everyone. Today we're going to go through 15D today. Looking for identities of Pascal triangles. This whole topic basically looking at proofs of Pascal triangles. The first three questions I haven't done before. There's calculus. If we haven't started calculus in 2 units, so I don't think we can do that one. So we're going to do. We're going to focus on the rest of it. Okay. I also attached a Eddie Wood's video in it. He did a really good proof. Quite simple. You can have a look at that one. It's pretty short too. So have a look and hopefully helps you understand a little bit more. So I'm going to quickly go through what it means first. So to prove Pascal triangle, there's something we need to do here. So I'm just going to put a table on the side here. Pascal triangle just slightly tilted to the sideways. Instead of a pyramid, it's like a slide. Okay. So the reason doing that is we have row and columns. You always start from zero, so from zero row, and also from the serial number, the and then first, second, third. Yeah. So first row is zero, so it's we add them all together, so total. So the first row total of 1, second row total of 2, third is 4, and then 4 plus 3. No. 4 plus 3 is 7 plus 1 is 8. That would be 16. 32 and 64 and so on. Okay. You probably realize they all double each other, but it's not a linear, more like exponential. Okay, so it looked like 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, and 2 power 5, and 2 power 6. Okay. So this actually what this whole lesson is about. So if we write an equation way, we basically need to prove this. The first number plus the second plus the third plus 4 all the way plus to the last one equals to 2 to the power of n. N is which row that is. Okay. So the first row, the total will be 1. The second row total will be 2. The third row, which is zero row, first, second, third, fourth, fifth, sixth, is the total. The total of the coefficient is 2 power of the number of the row. Yeah. To prove that, it's actually quite simple. Edward's video is got a little bit more depth into it, but I can just quickly prove this to you right now. All we need is what we learned before, 1 plus x to the power of n. Yeah. If we expand that, it will be n choose 0. Always start from 0. Yeah? Plus n to the power n choose 1, x to the power of 1. So x plus n choose 2, x squared plus n choose 3, x to the power of 3, and all the way to n choose n, x to the power of n. Okay. There's only one more step, and that's it. We substitute x equals to 1. So on left hand side, 1 plus 1, what's 1 plus 1? 2. Okay. 2 to the power n equals 2. Because x is 1, so x squared, x power 3, x power n, they're all 1. So basically 1 is eliminated. The order x is eliminated. Just have the coefficient left. All the way to n choose n. Okay, we just prove that. That's probably the simplest, easiest proof for Pascal triangle, for identity for Pascal triangle. So, hope it makes sense. Okay. Let's move on. So again, we're going to skip question 1, 2, 3 because it's calculus. We're going to go to question 4 was a little bit too easy, so I'll let you do it yourself. Question 5. This is something that we haven't go into before is sets. So a set, we need to see how many elements they have. They can't be repeated. Okay. So a set, we got 4 elements here. Okay, so we got A, B, C, D, 4 letters. Okay, so for a subset is anything that within the set, like anything that it can be. So it can be 0 elements. Okay, so nothing. Okay, and then 1 element, in T, 2 elements, 3 elements, and 4 elements. Okay, so from 0 all the way to 4 elements. So I'm going to quickly list them out. So for no elements, basically just empty, nothing in there. We got 1. Oopsie, black. We got 1. 1 elements, we can get A, B, C, or D, so we got 4. 2 elements, you can get A, B, A, C, A, D, B, C, B, D, or C, D, so you got 6. For 3 elements, you can get A, B, C, A, B, D, A, C, D, or B, C, D, so you got 4. And then all elements, you only have 1. Okay. Have a look at this. It's basically combination. So you have 4 element choose 0 is 1. 4 element choose 1 is 4. 4 element choose 2 is 6. 4 elements choose 3 is 4. And 4 elements choose 4 is 1. Basically combination. So if you add them all up, so total is 1 plus 4 plus 6 is 11, 15, 16 is 16. So 2 to the power 4. We basically just proven that. So B is done. And C, for C, explain why that happened is basically just ask us to prove it. We can just use exactly the same way to prove down here. Oopsie, why I need to go so far for? Just need to go down all the way down here. Okay, so yeah, that's simple. You can use exactly the same method to prove that or explain. Okay, now let's look into something slightly more difficult, which is this. Combination here, we need this equation here. This is the key for this whole question. Okay, alright, let's have a look at it. So we also to prove an equation, we normally use the left hand side. So left hand side equals to n factorial over r factorial n minus r factorial plus n factorial over r minus 1, oopsie, factorial n minus r plus 1 factorial. Okay. Something interesting here, r factorial and r minus 1 factorial. R factorial is basically 1 bigger than r minus 1 factorial. So r factorial is equals to r minus 1 factorial, the rollback method. You got r minus n minus r here and r minus n minus r plus 1. So n minus r plus 1 is 1 bigger, so it's n minus r plus 1 times n minus r factorial, isn't it? So let's substitute that in. So you got n factorial over r minus 1 factorial, you can match to the second one, and then n minus r factorial plus n factorial over r minus 1 factorial, match the same thing, and then n minus r plus 1 times n minus r factorial. Okay, so we got common factor here, common factor here. So all we need to do is just times each other by the thing that we don't have, times n minus r plus 1 times n minus r plus 1. Then we can have common denominator. This one here times r. Okay, we have a common denominator as n times n minus 1 factorial times n minus r plus 1 times n plus r factorial. Okay, the top bit we got n minus r plus 1 times n factorial plus n r n factorial. Okay, we can see that n factorial is the common factor on top, so we can take the n minus 1 out and then move on with that. So if we do that, the top will look like this, and then you can see r and negative r and I can cancel each other out, so that's what topic is. But for the bottom bit, if you have a look at this, this thing here and this thing here. It basically here we can go back this way. Okay, so r times r minus 1 factorial is r factorial. N minus r plus 1 times n minus r is n minus r plus 1 factorial. So we simplify that. And also at the top, n plus 1 is 1 bigger than n factorial. So we can, n plus 1 is 1 bigger than n. So we can do n plus 1 factorial on top. Okay, so that's what we got here, which is exactly what we are asked to prove, which is done. Okay, simple. Now the second part, I'm just copy that down here. We proved that already, but what does that mean? Now, it's a little bit hard to read if all those factorial fractions are here. Let me simplify that a little bit. You know that n choose r is n factorial over r factorial n minus r factorial, yeah? So that is basically this one, n choose r. Now second one, if we do r minus 1, so n is still on top, yeah, so n choose r minus 1. If n factorial on top, yeah, look right. And then you got r minus 1 as what r is in here, factorial. And then you need to use n minus r minus 1, yeah, so n minus, see, I need to use a brace here, r minus 1 factorial. Okay, if you open a bracket here, will be n factorial over r minus 1 factorial n minus r plus 1, because when you open a bracket it becomes plus, which is exactly the same as here. So it's n r minus 1, and choose r minus 1. The last one here, a little bit complicated. So if it's a similar fraction, we can if it's a similar thing, we can just do exactly the same, yeah. So instead of n elements, you got n plus 1 element this time. Choose r, so it will be n plus 1 element on top, so n plus 1 factorial over r factorial. Right, so it will be the whole thing on top minus r, yeah, n plus 1 minus r. Oh, if you rearrange it, you get n plus 1. See, if we rearrange it, we're around the bottom. You got n plus 1 factorial over r factorial n minus r plus 1 factorial, which is exactly here. So n plus 1 choose r. It's probably hard to read, but what we did is we proved that n choose r plus n choose r minus 1 equals to n plus 1 over r. Right, it's probably a little bit hard. It's still a little bit hard to see what it proved, but if you click a few numbers, let's say n row is, let's say it's a fifth row, and r is a second number. Okay, not the second number. Okay, so r minus 1, n choose r, so 5 choose 2. 5 choose 2 is 10, so 10 plus n choose r minus 1. R minus 1 is minus 1 is 2 minus 1 is 1, so it's 5 choose 1, so this one number 5 here, okay, equals 15, yeah. 15, well, let's ignore that part first. N plus 1 is 6, choose r, use 2, 6 choose 2, 6 choose 2, this number here, oh, 15. What a coincidence. What does it look like? The top two add together is the bottom one. It's basically the same as what we did before about Pascal triangles. So remember 1, 1, 1, 1, 2, 1. The top two add together is the bottom one, yeah. So we basically prove how we can construct a Pascal triangle. So yes, that's what it besides proven, which is another form of Pascal triangle identity. Okay. So I hope it's clear for you and is helpful. So for this exercise, I will get you to do 4 questions as homework, and hope you enjoy this video. Thanks for watching.